so in lecture 3, we started the discussion of measurements and projections. A key theorem that we went over was, if my handwriting is, by the way, not legible, just ask. The theorem, THM, I often mean theorem, is the eigenvalues of Hermitian operators. Hermitian operator is an operator that's equal to a stagger, are real, and the eigenvectors of different eigenvalues are orthogonal. We also said that the eigenvectors of Hermitian operator span the full Hilbert space. So based on this theorem, you realize that you learned that the eigenvectors of a Hermitian operator form an orthogonal basis for the Hilbert space, and often it's convenient to normalize every vector to unit norm so that we get an orthonormal basis. Why do we do that? Anyone? Do you guys know why we normalize it?
So you don't have to have a bunch of coefficients floating around.
Yeah, there's no physics associated with overall constant that sits in front of a vector. If you multiply all vectors in the Hilbert space by a coefficient, by the same coefficient, there's no physics associated with it. However, if there's a relative coefficient between two vectors, that is physical, right? Okay, so that is why we say, sometimes mathematicians say that we're talking about rays as opposed to a vector, right? Ray is just something like a vector that the length of it doesn't matter. All right. We said that, we said this, we proved this theorem. The reason we did that was that we said in quantum mechanics, we're going to measure, we're going to model observables, things we could observe as Hermitian operators. So then we said that because there's an orthonormal basis for the eigenvector form an orthonormal basis, I can take a Hermitian operator and write it in terms of its eigenbasis, in terms of the projections corresponding to its eigenbasis. And in this basis, the matrix is diagonal. And these are the eigenvalues, and these are the eigenvector, eigenket, and eigenbra, right? So this is a diagonal matrix. Every self-adjoining every Hermitian operator in the basis of its eigenvectors is always diagonal. As I said, we make them unit norm, so that our basis is orthonormal. We said that this is a projection, ket A bra A. Now I'm going to give you I gave you another more general definition of projection. An operator pi is a projection if it's Hermitian, and on top of it, it squares to itself. So this is a projection, you could check. But if you take two projections that are orthogonal and add them up, the result is also a projection. So this is a little exercise for you guys. This is a little exercise to check that this is a projection, meaning that this guy checks both of these conditions. So this is a one-dimensional projection. This is a two-dimensional projection, right? Now, if you add as all of the all projections corresponding to eigenvectors of a Hermitian operator, what you obtain is the largest projection, otherwise known as the identity operator. This is called a resolution of identity. This equation is very, very useful, and it underlies this modeling of observables in quantum mechanics or by matrix multiplication. We said that if you take this some operator and look at its ket bras, right, in some orthonormal basis, what this thing is, well, if these two, if A and A prime are the eigenkets of A, then this is just a diagonal matrix. This is just proportional to delta A prime, right? However, if instead of A, I put just some other operator, X, or I think previously I called it O sometimes. what this is a matrix element of O in the A basis, right? Any questions about this part? So resolution of identity, if we can now read that. Good. Yes, other questions? Then we describe measurement. I can't emphasize how important this slide is and how magical this slide is. The origin of all the counterintuitive things about, well, a lot of counterintuitive things about quantum mechanics is precisely this slide. So imagine you're measuring some observable, which is a Hermitian operator. It's a Hermitian operator as a matrix. If it's a matrix, is self-adjoint, meaning that if you transpose an element by element takes complex conjugations, you get the same answer, right? Okay, so we're gonna measure some observable A, and the state is initially in some ket alpha. We said that kets represent, these are complex column vectors that represent states of the quantum system. So when you measure some ket alpha, when you measure some observable A in some state alpha, ket alpha, there are D different outcomes. D is the dimensionality of the Hilbert space. If you're dealing with qubits, right, this would be two outcomes. For example, SZ, which was the Z component of the spin of silver atoms. There are just only two outcomes. These are independent outcomes, A1, A2, all the way to AD. If you have AI outcome, the probability of getting that outcome is bracket AI alpha, absolute value of its square. So as you probably know, because these are complex vectors, the bracket could be an imaginary number, or in general, a complex number. So when we take the absolute value squared, we're guaranteed that the probabilities are going to be always positive numbers or non-negative numbers. They might be zero. After this measurement, if this is the outcome of the measurement, the state is going to be in this ket, in this state. So measurement, in a sense, affects the state. It's not, measurement is not a perfect reader of the characteristic or whatever we're observing. It throws the state into some eigenket, right? And we said that this probabilistic behavior is an intrinsic property of quantum mechanics. You might have heard this famous quote by Einstein, God doesn't play dice. It has to do with the fact that quantum mechanics, based on quantum mechanics, is this phenomenon of observing something is absolutely and intrinsically and inherently probabilistic. It's as if there is some, like somebody is flipping coins or rolling dice, right, to decide. There is no way, it's not a question of how good our measurements are. There is no resolution to nature beyond this. These probabilities, you will never be able to do better than just these probability distributions, right? Okay. The outcomes of the measurement, the values that we measure are called eigenvalues. They are the eigenvalues. The components squared are the probabilities, and the eigenvectors are the states that we are thrown in after measurement. We talked about the expectation value, which is the sum of each outcome with its corresponding probability, right? This is the column of P of A or P of AI, right? And we saw that using the resolution of identity, you could write it this way. Or actually, you don't need to use the resolution of identity, just multiply these. Good? Any questions about this? All right. So we start working out an example, and because I was trying to work towards the origin of complex numbers in quantum mechanics. In this simple example of Stern-Gerlach, we sort of running out of time, so I stopped. Now I'm going to go over what we didn't finish last time. So what is the idea? This is some initial state that we're describing by 2x2 complex vector, alpha plus and alpha minus, right? And the goal of right now is to describe this Stern-Gerlach experiment, right? You're feeding alpha as the input of a measurement. There were two outcomes. And if you recall, with the key part of Stern-Gerlach was that we first measured S of X, took one of the outcomes, send it through the measurement of first measured S of Z, I apologize. Then send it through measurement of S of X, kept, for example, +1, and then send it again through measurement of S of Z, and then saw that both of the outcomes can come out, right? So what we're gonna do is we're gonna try to reproduce this physics that we observe using the rules that we have so far, right? For observables and vectors and this measurement rule, and we'll see that we must use complex numbers. There's no way around it. Okay, so is the principle clear what I'm going to explain? All right. Let me pause. Are there questions? So let's start with the first step, which is measuring S of Z. When initially the state is in ket alpha. So there are two outcomes, h bar over 2 minus h bar over 2. To make my life easier, sometimes I just say plus half minus half, right? The probability for this +1 is alpha plus squared, right? The component corresponding to the plus vector. If you remember, this was just 1, 0, and this is 0, 1. These are the unit norm eigenvectors of S of Z, right? And the expectation value is this. Is this step clear? So this is the very first measurement, right? So just this step. With probability alpha plus squared, the state is thrown into this ket. With probability alpha minus squared, the state is thrown in this ket. Next, we measure S of X. So, but if you recall, I said here, I'm just going to discard the -1 possibility, minus h bar over 2, and just keep this ket, states that are in this, then measure S of X, right? This is what it means. So I'm going to take as my plus, I'm going to take as my input S of Z of plus, and try to measure S of X. So repeating the same logic, right? So just now in this step, what comes in is S of Z plus. This is the input. We're going to measure S of X, and then you're going to get +1 minus 1, right? So you're going to get, so I usually write S, I was writing S of Z plus with plus, right? You're going to get the result S of X, result -1 for S of X with probability, which is the bracket of these two vectors, right? The component of S of Z plus in S of Z minus, S of X minus. This is the negative eigenvector of S of X. You get the result plus with this bracket. Now, what did we see in the experiment? We saw in the experiment that when you send S of Z plus with probability half, you got +1. With probability minus half, with probability half, you got -1. So whatever these numbers are, these complex numbers are, the absolute value of them is going to be 1 over square root 2, right? Because if you square it, you're going to get half. So let's pause here. Are you with me so far? Any questions?
I'm wondering, so in that last blue line,
Yes,
you were writing S of X, comma, minus in the bra or the ket, whereas usually if you were talking about just S of X or just S of Z, you would just put the plus or minus in the ket, but in this case, you're putting that there to
yeah,
indicate.
okay, so let me elaborate on that. So far I've been using this concise notation, right? Because I was focused on measurements of observable S of Z, right? And the eigenvectors of S of Z are these guys. If I wanted to keep the full notation, this is not clear enough. This is the plus one eigenvector of S of Z measurement, right? So every time you have an observable A, right? So actually, you see, this is the core idea. I was writing, this was the eigenvalue equation I was solving, right? So how did you know that this A is the eigenvector of A? It's just a compact notation. I was using the small letters to tell you that this is the eigenvector of A. And when I wrote B, for example, you knew that this is an eigenvector of B, right? Now that I'm using the notation plus and minus, it's not quite clear if this plus or minus correspond to measuring the Z component of the spin, X component, or Y component. So to be very clear, I'm using this notation to refer to S of Z components, right? If I want to be very, very precise, this is what it is. So for other measurements, I have to put the measurement next to it. Is that clear?
Yes, thank you.
All right. Sorry about the compact notation. And I insist, it might seem ultra compact and confusing, but I assure you, it really, really helps you. Otherwise, quantum calculations get out of hand. Yes.
Can you also use like up arrow for the plus Z and then just plus for the plus X?
There are, yeah,
That way
you
you
could
don't
use all sorts of notations. So this is the first course in the quantum mechanics that I don't know if you've taken, you might have taken other courses, but in this course, this is actually not the standard notation. This is a notation that is first clear, is good for this course, but as you go along, you're going to learn even a more compact notation. So people who do calculations use even a more compact notation. But yeah, for now, we're just sticking with this. So if I write, every time I write ket plus or ket minus, this is SZ plus, SZ minus, right? That's just my convention. I'll try to write SZ plus minus every time. You could use all sorts of notations as long as it's not ambiguous. Good. We said that the ambiguities of this notation is in degeneracies, and I'll explain that actually today. All right, any other questions? So you're with me so far. Good. Here comes the interesting part. Well, actually, all of this, we're going to go through some algebra, and you're going to see the result is going to be somewhat confusing at the end, interpretation-wise. Otherwise, the algebra is pretty straightforward. So because, what does this mean? It means that whatever the ket Sx plus is, I can expand it in terms of Sz plus and Sc minus, because they provide an orthonormal basis. The component of Sx plus and S and X, the absolute value of it has to be 1 over square root 2. Hence, I put 1 over square root 2 here. Right? However, there could be a relative phase in between them. I could have put the relative phase here. That is conventional. But there could be an e to the power of I delta 1 here. Why a phase and not an arbitrary complex number? Anyone? Can I put two
when you
I
take the
here?
complex conjugate, it cancels out when you multiply them.
Yeah, so that this vector remains unit norm. If you put 2i here, right, the norm of the vector would not be remain unit. So your probabilities will not add up to 1. Good. For those of you guys who are very comfortable with linear algebra, this is nothing but rotation. This is really nothing but rotation in the complex plane. Okay. And of course, the eigenvectors, this equation is reminding you that the eigenvectors of S of X are orthonormal, right? So S of X minus also has to, from this equation, also have to have the same form. There could be another phase here. However, the requirement that these two guys are orthonormal, or are the bracket of them is 0, tells you that this coefficient has to be minus e to the power of I delta 1. So there's some little calculation you could do to check this, right? Check. Oops. Is it clear so far? So these two equations, which are these two equations, which were the consequences of what we saw in measurement, outcome of Sx being +1, probability half, outcome -1 for S of X, probability half, and the fact that these probabilities are the components of the vectors squared, norm of the component squared, tells you that S of X plus must take this form and S of X minus should take this form. And as before, if you recall, we said that every self-adjoint Hermitian operator is diagonal in eigenbasis. So here we go. This is diagonal in eigenbasis, right? And if I expand the S of X, if I write S of X in the eigenbasis of S of Z, it looks like this matrix. Can you guys tell right away what this matrix is? So this is H bar over 2. Anyone? Can you tell me what this matrix is? Let me work it out. So what is plus? It's 1, 0. What is minus? Is 0, 1. This is an outer product. So it gives you 1, 0, 0, 0. Right? This, you do it and it gives you 0, 0, 1, 0. Therefore, this matrix is e to the power of minus I delta 1, e to the power of I delta 1. The things I don't write are zeros. It's conventional that you don't write the zeros. Good? Are you with me? Questions?
I have a question.
Yes.
If you go back up to, I think it's the previous slide where you're measuring measuring S of X.
Yes.
This to me looks like you're finding probability, but there's no squared. Or is this
So you see,
is this the
okay,
absolute expectation value?
if this guy squared is 1 over 2, right? I just took the square root,
Okay.
right? Clear?
Yeah.
Good. That's a good question. If sometimes I might just skip lines of algebra, please ask. Any other questions? We gave these operators names, by the way, in the last lecture. Do you remember what they were? S plus and S minus. All right. Good. All right. So far, so good. So far, you might say you don't have to use complex numbers. Why is that? Can anyone tell? Because delta 1 is up to me to choose. So what is a choice of delta 1 that would make this matrix real? or make these vectors real? Any thoughts?
Essentially some integer multiple of pi.
0, for instance. Right? So e to the power of I0, that's just 1. E to the power of minus I0 is 1. So I could just write plus, ket plus, plus, ket minus, ket plus, minus ket minus. Or I can pick delta 1 to be pi. In which case, this will be minus 1, this will be plus 1. Good? All right. Now, here comes the problem. Spin has 3 components. So I also can measure S of y by rotation of the Stern-Gerlach measurement device. Now, what happens is by symmetry, because I could just, whenever I set S of x, I could imagine I'm measuring S of y. By symmetry, I should have S of y ket plus, which is the eigenket corresponding to outcome plus 1 for S of y to be this, and the outcome for S of minus 1 for S of y to be this, with a new coefficient, right? It doesn't have to be the previous coefficient. Is that clear? I just renamed what was x. I called it y, right? And the result of the measurements are still the same. Now, you could call z x and call, and then do the measurement of x going to y. You should have these equations, right? I'm just renaming symmetry. Like this is a 3-dimensional thing, so I could do the experiment. So, you know, like I did measurement sz followed by x, and I got probability half for these. But the thing is, if this is sz sy, I get the same results. If this is sx sy, I get the same results. You could, if you're not a believer, you could just do experiment, and experimentals do these experiments, and the result is just plus 1 minus 1. This was actually part of that thing that was, it has to do with the results being quantized, right? We said the outcomes of the measurements were always quantized. Whereas if this was an actual vector in space, when you project it, you don't expect the vector to always get projection of the vector to be always plus 1 minus 1 in all directions, right? That was the very first bizarre behavior that we observed in Stern-Gerlach. All right, so what does that mean? We have already defined what these kets sx plus minus are and what sy plus minus are. So this is a consistency check. We must satisfy this relation, right? There's no new variable to introduce. All right, so let's try to satisfy this relation. You take this inner product based on the equations that I showed you above. You obtain that 1 over square root 2 has to be half 1 plus minus e to the power of I delta 1 minus delta 2, which tells you that delta 2 minus delta 1 is pi over 2 or minus pi over 2. There's no other way of solving this equation. So, what do you find? You found that this is the origin of complex numbers in quantum mechanics. If you set delta 1 to 0, so that your vectors, your kets of sx plus minus don't involve complex numbers, now delta 2 will be e to the power of I pi over 2. What is e to the power of I pi over 2? Anyone? It's I. E to the power of minus I over pi over 2 is minus I. If one of them, you force it to be real, the other one must be imaginary. There's no choice. There are no choices. All right, this is an important, I cannot stress this enough. This is a very, very important thing in quantum mechanics. We must use complex numbers. And Stern-Gerlach makes this evident. Like this is there's a set of lectures by a very famous physicist, Sidney Coleman at Harvard, and his lecture notes were called "Quantum Mechanics in Your Face." So Stern Gerlach really confronts you. It's like complex numbers are inevitable, and I absolutely encourage you guys to think about, try to come up with some sort of a setup where you could avoid complex numbers. It's not possible, just based on the logic that I. All right, any questions? This was what I was planning to finish the last lecture with, but we ran out of time. Any questions?
What's the generalized version of this? Like, that doesn't like, is it about the number of dimensions of your observations on space? Like, the general rule that we need to have complex numbers since we have X that doesn't relate to Stern.
You mean a D level, a measurement with D outcomes? Is that what you mean? What do you mean by general?
Like it seems like this argument is dependent on the fact that like we have these Sx and Xy operators, but can we generalize this to like quantum mechanics in general? Like because we have this structure, we must need complex numbers.
Yeah, so exactly. So let's just, okay, let me run the argument this way. Let's say you don't care about the grand theory of nature. You're an experimentalist, you only observe silver atoms, and you want to explain silver atoms. This measurement forces you to use odd. All right, so you model that. Then you go do another experiment. Every single time, you're forced to introduce these guys by the same logic, exactly by the same logic. Now, there are setups where you might get lucky and you get away with real numbers. But in general, it's complex numbers. And in general, complex numbers suffice. You don't need anything fancier. Now, I will get to very soon, hopefully today, I'll get to the point, I'll get to the setup where you can get away with real numbers. I'll explain when is that. All right? So it is conventional to pick S of X delta 1 equals 0 and delta 2 equals pi over 2. This way, at least S of X plus minus are real, have real coefficients, but this guy has an I. You could pick another convention, that's okay. But this is a Wikipedia level convention that everybody uses. All right, any questions? So, all right, this complex numbers is really responsible for the phenomenon of interference. If you were working with real numbers, you would never have interference. It's hard to see for now, based on what I've told you, but I encourage you to think about it. One way to actually get these quantum mechanics by hard to make it simplify it, like not, like describe the experiment using a simple set of rules, and you will fail. All right, so based on what I've told you, this is S of Z, right? H bar over 2 plus plus minus 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 minus, right? These are the eigenvectors, and these are the +1 and the -1 are eigenvalues. What this expression is simply is precisely this, right? So here I'm writing this for each of these observables, right? Now you could check that these observables are, all of them are Hermitian. Hermitian means what? It means that if you transpose and take the complex conjugate, you're going to get the same matrix back. These two, S of X and S of Z, are real. So you don't need to take complex conjugate. And you see explicitly that they're equal to their transpose. Right? This guy doesn't have off diagonal. This guy has off diagonal, but it's equal to its transpose. Now this one has if you take the transpose of this one, you multiply this by -1. However, when you take the dagger, which is transpose followed by complex conjugation, this guy remains the same. It is a Hermitian operator. Good. These matrices have a name. They're called Pauli matrices, after Wolfgang Pauli, one of the very influential people in the early days of quantum mechanics. Good. Any questions? Now, here comes perhaps the most important algebra in quantum mechanics. These matrices, Pauli matrices, satisfy interesting commutation relations. So, commutator of two matrix is, this is the notation we use, is AD minus BA. This is called an anti-commutator. We usually write it with curly bracket. This is AB plus BA. This is symmetric. This is anti-symmetric. All right, question. If A and B are observable, is the commutator of AD an observable? Any thoughts? How would you check whether the commutator of AD is an observable?
Check if
You will
it's
have to-
Hermitian.
Yeah, you'll have to check this complex conjugate and check to see whether it's equal to itself. Now, let's take the complex conjugate of this guy, right? Let me just write it here. I'm going to take the complex conjugate of the commutator. Good. So I'm taking the complex conjugate of AB minus BA. Recall, so this is AB minus BA. But if you recall, when you take the dagger, the order changes. The same as transpose. This is what? This is B dagger, A dagger, minus A dagger, B dagger. Right? But then we said B and A, I assume they're Hermitian, they're observable. So this is BA minus AB. Is this equal to itself? Is the dagger equal to original one? No. This is minus the commutator. So it's anti-Hermitian. The commutator of two observables is not an observable. The anti-commutator of an observable is an observable. Is this clear? All right. So these relations, I cannot stress them enough. These are the core. This is a very, as usual, very compact notation for the algebra that these guys satisfy. The algebras are the set of these commutation relations, right? We usually don't worry about anti-commutation relations, but these matrices are so nice that the anti-commutation relations are also very neat. So the commutator of Si and Sj is I H bar Sk epsilon Ijk. Epsilon Ijk is a totally anti-symmetric symbol. It's a tensor with 3 indices, and the convention is that 1, 2, 3 is +1, and all its cyclic permutations are also +1. 2, 1, 3 is -1, and all its cyclic permutations are -1. Good? Are you guys familiar with the anti-symmetric tensor, totally anti-symmetric tensor? So first question, what is 1, 1, 2?
0, right?
0. Why? Because it has to be totally anti-symmetric. If I swap these two, it should become negative of itself. But if you swap it, epsilon 1, 1, 2 remains epsilon 1, 1, 2. Therefore, it has to be 0. Now, what is 3, 1, 2. Is plus 1. Why? Because it's a cyclic permutation of 1, 2, 3. All right. I trust you guys, you could do these. So to follow quantum mechanics, you shouldn't read it as newspaper, right? Like you should do a little, you should have a notepad or notebook or iPad right next to you and do these little calculations to just convince yourself that these are how things work. Good? Any questions? So one thing
Yeah,
that's
so
yeah. Uh-huh.
So we can understand like the commutator as like letting us know about whether we can know two things simultaneously, have full knowledge
Yeah.
simultaneously. But what about the anti-commutator? Is an intuitive understanding of that?
Not for today. The quick answer is there's no simple way of describing at this level of quantum mechanics because I haven't defined for you guys bosons, fermions. It's a question of statistics. So at this point, commutators are the only things that we care about. Anti-commutators are just some relations that these matrices hold. Satisfied. All right, that's a very good question. And as I said, you guys have a lot of. I'm pretty sure you guys have a lot of questions, but sometimes you just have to hold on to this, and then you will eventually learn about bosons and fermions. Actually, quantum mechanics will force you to talk about bosons and fermions, and then when you talk about fermions, you realize that this is a nicer thing to consider. But that will have to wait until much later. Hopefully, the last section of this course, we will get to bosons and fermions. All right. Okay, I have to speed up because I have 29 slides and I'm slide 10. Now, it is helpful to define non-Hermitian operators, S plus and S minus. I defined them before. What these guys are, these are Sx plus minus Isy. Good? There's also it's also very, very helpful to define the total spin square. If spin were a vector in space, this would be the norm of vector square, the length of the vector square. This is an observable called S2. You could calculate this just based on the matrices. You know what S of X is, S of Y is, S of Z is. These are Pauli matrices up to H bar over 2. You add them up, you obtain this. You obtain 3 over 4 H bar squared identity. So what does this tell you? What does this tell you about the commutator of S2 and the Pauli matrices? It tells you that it commutes with everything. Because it's identity. Identity operator commutes with everything. Is that clear?
Can you repeat that one more time?
So add these 3 things, right? So just you know what these matrices are. You get a matrix which is proportional to identity. Identity and any matrix commute. Why is that? Identity and any observable, as a matter of fact, identity and any operator commute, any matrix commute. Why? Here it is. Take some arbitrary matrix I. What is the commutator? This is Ix minus X identity. What is Ix? Identity X. It's just X. What is X identity? It's X. So identity and every matrix commute. Now, if you multiply identity by number, it goes for the right. It's just that number multiplied 0. So S squared, is that good? Make sense? So
Yes.
S squared commutes with all the Pauli matrices. So this is an crucial point. I don't know how many of you guys know about group theory. but this is an incredibly important fact in group theory that really revolutionized mathematics and like what is called physics, actually, physics quite a bit in the second part of the 20th century. These appearance of group theory in physics was crucial. So actually, I teach quantum field theory in the afternoon, and like I start with group theory. It's very important. Group theory is all over the place. But these are, if you have taken group theory, these are familiar. Good. Are we with me? It's all good. Does it make sense? Okay. Degeneracies. What was a degeneracy? We say an observable is degenerate if it has, so sorry, let me back up. We say a Hermitian operator, aka observable, is degenerate if it has eigenvectors, different eigenvectors with the same eigenvalue. So an eigenvalue is repeated. This is where our notation gets a little bit problematic, right? Because we're writing this equation, right? Now, what I'm saying is that it is possible for two eigenvalues to be the same when the eigenvectors are different. So this notation is not very good. This is the setup of degeneracies, right? So what we should be writing is, for example, consider two vectors, ket A1 and A2, which are inequivalent, but they have the same eigenvector A, eigenvalue A. So these are degenerate. What do we do in these situations? One way of doing it is to write it this way. So instead of write it as ket A semicolon 1, the first eigenvector corresponding to eigenvalue A, right? And this one, the second eigenket corresponding to eigenvalue. So in general, you could think of, in the presence of degeneracies, you should be using this. And as a matter of fact, you should be using alpha of A, because different A's could have different degeneracies. These numbers that we use to describe a ket are called quantum numbers. Is the notation clear now?
So what was the point about the alpha sub A?
Yes. So imagine a setup where you have the following setup. You have A1, which is not degenerate. You have A2, which is degenerate. Right? So I'm going to write it this way. So I have total of 3 eigenvectors. So how am I going to use a notation for this? This guy needs an alpha, This guy doesn't. So I'm just going to put alpha of A. When A is 2, alpha of A runs from 1 to 2. When A is 1, alpha of A just takes one value. Right? Because different eigenvalues that have different degeneracies. Does it make sense?
Got it.
Good. Any other questions? Oh wow, I'm running really behind. Okay, it's all right. We'll all get as far as we can. It's okay. Any other questions? I would rather you guys ask questions than me just go ahead.
Is that a J or a semicolon?
Semicolon.
Okay. Thank you.
Sure. Unfortunately, my handwriting is so bad that writing on the chalkboard might have some similar problems. So thanks for asking the question, because probably someone else has the same question. All right. Good. Now, this is what I was hoping I can finish in lecture 3. So now we're starting lecture 4. So it's a good moment to pause. So what did we go over? We talked about how it's inevitable to use complex numbers. We tried to model Stern-Gerlach using two-dimensional Hilbert space, two-dimensional complex vectors, and we saw that the natural description of the three quantized observable you had, the z component of the spin, x component, and y component, was in terms of 2x2 matrices that we wrote as Pauli matrices. These Pauli matrices, you should know them by heart for sure. Here, up to h bar over 2. I'm just suppressing h bar over 2, all right? This is s of z, s of x is this, and s of y is I. Actually, I think this is the convention. I think if you look up Wikipedia, they put h bar equal 1. So they put half, multiply all of these matrices by half. They're called Pauli matrices. It's the simplest way to model the Stern-Gerlach experiment. Good. Then we talked about the algebra these guys satisfied, commutators and the anti-commutators, right? The commutation relation. What is the commutator of S, X, and SY? Anyone? What was it? It was I H bar That's why I say you have to do these things for a step later. Oh, sorry. Whoops. I. Now let's call X 1, Y 1. Oops, sorry. Yeah, actually, that's how I want to do it. Z1. Anyway, this is do this for yourself. You're gonna get ISZ. I think I just want to go forward. But you should be doing these little calculations. Each of them takes like 30 seconds or a minute, but it's important that you do this. All right. So now we are gonna talk about commutators. The notion of a commutator has many layers in physics. In briefly, when two observables, sorry, let me back up. The Stern-Gerlach experiment, what it showed us was that there are observables that could not be simultaneously measured. Now, first, let me tell you what the message is, and we're going to work towards it. The message is that if two observables commute, meaning that their Hermitian operators, Hermitian matrices that describe them commute, like A and B minus B of A is 0, they can be simultaneously measured. If they do not commute, they cannot be simultaneously measured. So the commutator of any observable with itself is 0. It means that you could repeatedly measure a single observable and you'll never find any inconsistency. S of X and S of Y do not commute. Remember, I told you matrix multiplication has the notion of order, right? Which measurement you do first. So when you have S of X, S of Y, that's like measuring Y first, then measuring X. When you do SY, S of X, it means measuring X first, then measuring Y. When they don't commute, it means that the order matters. If you could simultaneously measure things, the order cannot possibly matter. Think about that, right? If you could simultaneously measure observables, the order cannot matter. If the order matters, it means that you cannot simultaneously measure them. When the commutator is 0, aka you can simultaneously measure them, we call such observables compatible for obvious reasons. When the commutator is non-zero, they are incompatible. So here's a question. Is Sx and Sy compatible? No. Is S squared and S of x compatible?
Yes.
Somebody. Yes. Very good. So you could know the value of S of x and know the value of Sx squared plus Sy squared plus Sc squared with arbitrary precision. No problem. Good. Even though S squared looks like Sx squared plus Sy squared plus Sz squared, and you can't know the value of Sy and Sz exactly, you could know the value of each of them squared summed up. As I said, quantum mechanics has these counterintuitive behaviors, but the way to understand it, the route to understanding it is first understand how to calculate and gradually build intuition. All right? Good. All right. So a theorem. If A and B are compatible observables, there are Hermitian operators that commute, then the matrix elements of B in the eigenbasis of A are diagonal. B in the eigenbasis of A is diagonal. We said that every Hermitian operator is an eigenbasis is diagonal. Now here we're saying that if two operators commute, they could be written as diagonal matrices in the same eigenbasis. Is that clear? Let's pause and see if that's understandable. Right? If I have two diagonal matrices, the rest is 0 when I'm writing, right? The commutator of two diagonal matrices is what? 0. What this theorem says is going the other way around. Every time you have two operators that commute, two observables that commute, you could write them as diagonal in the same basis. Because they're observables, how do you find the diagonal basis for one of them? Just expand them in their own eigenbasis. Therefore, both of them are diagonal in the same eigenbasis of one of them. Clear? We're going to prove that in a second. It's a one-liner, but let's first let it sink in. What is it, right? Any questions? So how do you prove it? Assume ket A's are the non-degenerate eigenvectors of observable A. Let's write down let's consider the matrix elements of the commutator of AB in the A basis. So this is what this matrix element is. I have AB minus BA, right? Oops. So here I act with A on this guy, I get A. Why did I not write A star?
Because you're considering Hermitian operators.
Exactly. Because A is Hermitian, so this is A. Then for the second term, I act with A on A prime, so here's A prime. So this ends up being A minus A prime, this matrix element. This has to be 0, because we assume that the commutator is 0, which means that either this is 0 or this is 0. Therefore, we learn that in the absence of degeneracies, right, A not equal to A prime, these matrix elements are 0, they are simultaneously diagonalized. Another way of saying it is that the matrix element of B in AA prime is just delta of AA prime, BAA prime. It's just a repackaging of what I wrote up there. So now take B and apply a resolution of identity from the left in the eigenbasis of A and a resolution of identity in the right. What do you find? You get something. Act with that operator on BA. You learn that BA is this guy A because they share the same eigenvectors. This is an eigenvalue equation, eigenvector, eigenvalue, eigensystem equation for B. The eigenkets of A are also eigenkets of B. Now, why do I say that they could be simultaneously measured? I told you that measurements throws you into an eigenket. The point is that an eigenket of A is the same as an eigenket of B. So when the first measurement throws you into an eigenket of A, the second measurement is just repeating. It's not going to change your vector because it's still an eigenvector. Is that clear? So for this argument, it was essential that the operators are not degenerate. It's actually unnecessary. We were going to later see that the same result goes through even if they're degeneracies, right? So in summary, measurements, observables that could be measured simultaneously, right, are observables that could be measured simultaneously are commute, and those that cannot be measured simultaneously, they don't commute. Here's another way of understanding the necessity for complex numbers. If all observables we have commuted, right, we could write them as diagonal matrices in the same basis. These are observables. So the matrix elements could be complex. No. Diagonal matrix elements of Hermitian operators are real. If all of our observables could commute, we could always write them as a bunch of real diagonal matrices. There would be no need for complex numbers. It is essential. If you're using essential, it has to do with the fact that there are observables like Sx and Sy, Sy and Sz, Sx and Szx, Sx and Sz that do not commute. Is that point clear? I remember when I was first learning quantum mechanics, one of my big puzzles was why complex numbers? And it wasn't making so much sense to me, but like this is really in your face. You must just play around with it. Try to convince, try to cook up a setup where you're not using complex numbers. You'll see that it's impossible. All right, any questions? How am I doing on time? All right. Any questions? Now, for a second, let me use a stupid notation, which is I'm gonna write this ket. So this is stupid notation. I'm telling you it's stupid notation, but I just want to make a point. I'm writing ket A prime, comma, B prime. As in, this ket is simultaneously the eigenket of A with eigenvalue A prime and eigenket of B with eigenvalue B prime. This is redundant. Why do I call it stupid? Because it's redundant, right? Hopefully I made the point that it's redundant. So, good. Is that clear? Actually, I think here I'm using angular momentum. I could have used, yeah, okay. So here I'm relying on the fact that you have some knowledge of physics. You have taken some quantum mechanics at some point in your life. So I could replace all of these guys L's with S's. Actually, let me do that. Let me do that. I think that's probably wise. Yeah, this is good. So what was the spin that we were talking about? It was a quantum observable. Actually, let me call these L's. It doesn't really matter. But I think I want to stick with a notation which is more standard. I don't want to change notation. It was an observable that was coming out as a quantum, what was quantum outcomes. Now, it had two possible outcomes because the silver atoms had spin half. They had one free electron. There are atoms out there where you measure their spin or measure their angular momentum. There are more than two outcomes. As a matter of fact, if it has spin S or angular momentum L, what are the number of outcomes from your quantum mechanics?
L plus 1.
L times L plus 1, right? Oh, what am I saying? No, that's not right. That is not right. 2L plus 1. 12 plus 1 outcomes. What are the number of outcomes? Start from minus L, then minus L plus 1 all the way to 0, then 1, 2, 3 all the way to L. Right? When you spin half, what is the largest one? Is half. Then one by one, we go to, what's the next one? Is half minus 1. It's minus half, and you've reached the lowest point. There are two outcomes. Right? The number of such outcomes is 2L plus 1. Sorry, I misspoke there. Good. So the analog of this is like S squared, right? And this is like a Z component of it. This thing. They commute. So this is a generalization of what I was talking about, S squared and SZ. If you're happy, you could just pick L equal half, and these equations should be familiar already. Good. Remember, I wrote up here. S squared is 3 over 4 H bar squared, right? Where does 3 over 4 H bar squared come from? Let's come here. Our silver atoms had spin half, so half times half plus 1 is 3 over 4 times H bar squared is 3 over 4 H bar squared, right? This is the generalization of that. So now it should be clear, the notation we use is this. If L is the eigen, that is the quantum number of S squared, the quantum number of S squared is insufficient to describe the vector because there are degeneracies. To describe the degenerate things, you introduce a new variable. I think I previously I said there's semicolon like this. What is this? This is this example of I was talking about. So I'll just give you an example of the setup where A is insufficient to describe the ket because there are degeneracies. Here, A is the eigenvectors of, in my example, A's are eigenvectors of L squared, and these are the eigenvectors of LZ, right? They're simultaneously commuting operators. Is it clear what this example is? I'm giving you a physical example for this notation. It's nothing exotic. It's just a generalization of the Stern-Gerlach to the case where you have the outcomes have D possibilities. Spin is large. Good. Any questions? Oh, I'm running really out of time. Wow. All right. At least let me get to the. All right. So let me speed up a little bit because I have to end on a reasonable point. Imagine now that you have a set of observables that are simultaneously commuting. Then you could use a set of collective indices. These correspond to things like this, right? In general, this was for the setup where you had only two operators commuting, right? In general, there could be a whole set of observables commuting, right? So you will use these collective indices. There could be all sorts of indices. This is sort of redundant, as I said earlier, right? So there's like a more compact notation here. There will be a bunch of numbers. They're called quantum numbers, right? The numbers that you put in your kets to label your states by the eigenvalues of the simultaneously commuting observables. They are the quantum numbers. I remember when I was in undergrad courses on quantum mechanics, nobody ever defined what a quantum number was, or maybe they defined and I was not paying attention. But okay, good. And of course, you have the resolution of identity as a sum over all these things. So, like the orthogonality relations will go through as expected, and things are fine. I think I explained this earlier. All right, so let me pause here. Is the idea of commuting observables clear? Commuting observables is a mathematical statement about self-adjoint permission operators that we mapped it. We're using commuting observables to describe the setups in our Stern-Gerlach or whatever experiment where we could simultaneously measure things. What measurements could we do simultaneously in Stern-Gerlach? An example is S squared and SC, for example, right? So we would use commuting observables for that. Now, not all observables in quantum mechanics are commuting. In fact, quantum mechanics is interesting because there are non-commuting measurements. So when we said the lesson from Stern-Gerlach was that measurements affect your future, like the state could change the state. That occurs when you have observables that do not commute. The order matters. So they could they're called incompatible, right? SX and SC, for example. Incompatible observables cannot have a complete set of simultaneously eigenkets. Here's a proof. Imagine AB that are non-commuting have a simultaneous set of eigenkets that form a complete set. Here, the keyword is complete set. So when they act on ket A comma B, right? This B first acts here, give you B little b. A acts here, you get AB, AB. BA acts on it, you get BA, AB. So when you look at the action of the commutator and the simultaneous eigenket, you get 0. Right? If this equation was true for a set of kets A comma B that span the whole Hilbert space, a complete set of such kets, what do you conclude? You conclude that this operator is 0. Why? Because you have an operator called commutator of AB that acts on any vector for all size, gives you 0. What is that operator? It's a 0 operator. So it has to vanish. However, it is possible that the commutator is non-zero, but this action is 0 on a single ket. What does it mean? It means that I told you in general, there are measurements that are incompatible. However, meaning that the results of measurements could change the outcomes. It is possible that there might exist vectors in the Hilbert space that if you fine-tune things, the measurements don't destroy each other's results. I think I'm out of time. So what I'm gonna do is, I'm gonna just make a suggestion for you guys as a homework or a little exercise for yourself. to make sure this clicks, everything we've gone over today. Compute the commutator of Sx and Sc. Just calculate matrix multiplication. Find a vector such that this commutator, which you're going to find to be non-zero, acting on that vector gives 0. Then show that there cannot exist two such vectors that are linearly independent. This is the homework. Just make the idea of incompatible observables click. Now, I'm going to summarize this lecture and stop at the beginning of, okay, slide 19. All right. I'm just 10 slides behind. It's not the end of the world. Any questions before I summarize?
I have a question about is there
Yes.
some significance to like the L squared or the S squared? This operator?
Yes, absolutely, absolutely. It's the total spin of the particle. How do I know that the spin of and silver atoms is half? Because I've measured it, right? So there is some measurement, the outcome of which corresponds to measuring Sx squared plus Sy squared plus Sc squared. To perform that measurement, I don't have to first measure S of x, then measure S of y, then measure S of z, and score them and add them up. As a matter of fact, if I did that, I get nonsense because they don't commute, right? So there's a measurement that directly measures S squared. Yeah. So there are measurements. I'm not describing them yet.
So you can know the total, but not
Correct.
like two individual axes.
Correct. I understand that. I think it is essential. Next week when I'm back, it's essential that we have some office hours, and I encourage you guys to come to the office hours and come with questions. Right? Think about it, play around, find. Otherwise, quantum mechanics won't click. You just have to play around and get used to this algebra. So we'll plan the office hours. I'll announce everything on Tuesday, and we'll go forward with that. But it is absolutely essential. I cannot stress this enough, that you get used to the algebra. This is the only way to make sense of quantum mechanics. All right, with that said, what I'm going to do is I'm going to summarize and ask for questions because I'm running out of time. So what did we describe today? We talked about we tried to explain a Stern-Gerlach by modeling it with these two-dimensional vectors. We realized that we have to introduce complex numbers. We use a convention for eigenkets of the Sz, Sx, and Sy observables. This convention led to very explicit 2x2 matrices for Sz, Sx, and Sy observables. They're called Pauli matrices up to a factor of h bar, right? Then we talked about compatible and incompatible observables. Compatible observables are those that could be simultaneously measured, and incompatible are the ones that could not be simultaneously measured. Quantum mechanics is non-trivial because there exists observables that could not be simultaneously measured. All right, thank you so much. Are there any questions?
Yeah, I think we still don't have bright space, this course on bright space.
Yes, I understand that. Yeah.
Uh-huh.
So
how should we submit this homework?
You will be submitting it on Brightspace, and I will announce the first homework. I haven't announced the first homework. Next Tuesday, I said in class before. Next Tuesday, there will be the homework that will be announced. The Brightspace, all of that will work.
Okay, got it.
All right. Anything else?
Sir, do you know when the midterm is?
The midterm. This is whenever the midterm week is. So either the Tuesday or Thursday of it. Yeah. There's some flexibility on my side, but we'll discuss it. Whatever is the midterm time, in the vicinity, give or take a couple of days, we'll find. Any other questions?
Wait, I thought you said day one there was no midterm.
Oh, did I say that? Maybe. If I said that, there will be midterm. I don't recall actually.
Okay.
Whatever is in the syllabus, whatever is in the syllabus that I said earlier, because I'm teaching 2 courses. I might be getting.
Okay.
Yeah. Yes. Any other questions? All right. Thank you so much. I'll meet you guys on Tuesday. The first homework set will be announced on Tuesday. Bright will work. The TA and all of that will be coordinated. The office hours will be announced. And meanwhile, I absolutely encourage you guys, get your hands dirty. Don't wait for this. Just these little homework things, these light purple things that I write, work them out for yourself. Just play around with these matrix multiplication, commutation relations, anti-commutators, and so. Don't wait for the course will go fast. All right. Any last questions?